is definition is a to and fro repetitive response of a dynamic system. Of course, some of you would have already studied a course on vibration. They might have given you the definition of the vibration, isn't it? A static system cannot vibrate, so naturally it has to be a dynamic system. What is meant by dynamic system? If the behavior of the system changes with respect to time, it is dynamic. This is static, it doesn't change. So if the behavior of the system does not change with respect to time, it's a static system. So dynamic system is basically a system whose response changes with respect to time. It's dynamic system. So response of repetitive response. What is meant by repetitive response? I give some input, I get some response. That is once. If I give some input, I keep getting some responses. That is repetitive response. Okay, so that's a repetitive response. To and fro repetitive response means what? Let's say if I have a scale, and that's a typical example. If it's a scale, we give an impulse, a displacement, and then leave it. So the scale moves up and down with respect to a mean position. So to and fro repetitive response of a dynamic system is vibration. Okay. So as long as I don't give any input, it is a static system. I give some displacement, leave it. Of course, with a very stiff, you will have this is the behavior changes. Sorry, this behavior changes with respect to time, so it is dynamic system. It is to and fro and repetitive. See, every time it's for a long time at least the response is coming. It's not just one time goes up, one time comes down. It's repetitively coming, so it's a repetitive response of dynamic system. To and fro. This is a circular repetitive response. Probably you have a fan, you rotate it, continuously rotating. That's also a response changes with respect to time. That is continuously rotating in one direction. Continuously moving in one direction. It's not vibration. To and fro motion. Either it can be clockwise, anti-clockwise, like a disc rotating clockwise and anti-clockwise. That's also, we call it as vibration. Because it satisfies this definition. Why? That's called actually angular vibration or circular vibration or something like that. Okay, that is also called vibration. Why? It satisfies to and fro the clockwise and anti-clockwise movement of a disc hanging in a thread. You call it as vibration, right? So to and fro repetitive response of a dynamic system. Anything, if any movement or any phenomena that satisfies this, you simply call that phenomena as vibration. Okay? So that's the definition of vibration. And today our job is to study some of the sensor which can be used to measure this displacement or torque, force, temperature. These are all static parameters. So at a given time the temperature is so and so. At given time, I have moved this much distance. So it's all only one value, not very dynamic in nature. So it's very easy to quantify. The very first class we have seen definition of measurement. Measurement is an act of finding a number of numerical multiplier to the unit, isn't it? So it's that numerical multiplier means it's a one number that we have to identify to assign for that parameter. Whereas in case of vibration, we don't have a single number. We have a waveform. We say this is the kind of vibration that we have. With respect to time, the scale moves up and down, or this rotates clockwise and anti-clockwise. So with respect to time, the theta changes in case of angular displacement. In case of scale, the displacement changes. Y of t changes with respect to time, sinusoidally or in some fashion. It need not be perfect sine wave all the time. It can be a zigzag waveform also, but it is a waveform. the definition of measurement is, out of all this, we need to assign only one number to vibration, and then we have to try to at least express the vibration. Okay. So what is that we will basically measure in vibration itself is a big debate. So that's, normally it's a contextual based. Like if I'm an engineer, I'm looking for some information, I will basically decide what is that I'm going to measure. Okay. In general, some of the parameters commonly used for vibrations are all peak to peak value. For instance, if some vibration is there like this, from lowermost level to the uppermost level, what is the amplitude difference? I measure that. I express that as a number. For example, this is so much. Let's say 3.5, and then in acceleration unit you simply give some unit and then express that as a number for that vibration. If vibration is more, that number will be more. Peak to peak will be more. If vibration is less, that peak to peak distance will come down. So peak to peak measurement is one measurement that can be used for representing vibration signals. Yeah. Similarly, basically, if you take these vibration signals into a computer and then see, it's basically a time versus amplitude graph. So for every time instant, you will have an amplitude graph. So it will be a column of value along with time. If you have a column of time stamps, for every time stamp you will have an amplitude value. That amplitude value will be 0 here, keep on increasing. Let's say this is 5, this is minus 5. This will be 0.5, 1, 1.5, 2, 2.5 up to 5. Then 4.5, 4, 3.5, 0, minus 1, minus 2, minus 3, minus 5, 0, plus 5. Like that it go on. That number will be go on changing as the time stamp changes. Okay. So this is a perfect sine wave. So we may not take average. What will be the average of perfect sine wave? 0. So we may not use average for a perfect sine wave. But in real time, when you take a signal, this is for a classroom discussion I have taken, vibration signal will be like a sine wave. But actual vibration signal will not be like a sine wave. So it will be different. And in those cases, I can use even average as a measure of vibration. The average value of vibration. I'll show you some typical examples. Real machinery signals will look like this. This is the displacement signal. So if these peaks are small, all the peaks are small, that's a small vibration. If all the peaks are high, your average will be high, so you will have a higher vibration. So average is a measure of the vibrations. RMS value. What is meant by RMS? Root mean square. Okay, that's basically what? Ignoring the sign and then taking accumulation of all those values is RMS value. Okay. Basically, you leave the sign, square it, take a square root of it. It's ignoring the sign and then taking the cumulative value. So it's an RMS value. These are all some of the commonly used measures for measuring vibration. These are not exhaustive list. You can have your own parameter that you can use it for measuring vibration. For instance, in my research I used to use statistical features. Here average alone is one statistical feature. We call it as mean, arithmetic mean. The mean, standard deviation, glucose, skewness, minimum, maximum, standard error. There are 12, 13 parameters. We call it as statistical parameters that we use. Also, we might plot a histogram of vibration and then use histograms as a feature. So, you have plenty of parameters that can be used to represent vibration signal. Very primitive quantities are peak to peak value, RMS value, average. Okay. So, vibration is not a static parameter. It does not have a single value for a given measurement of time. When you take measurement of at a particular time, you take a measurement, it does not have a single value. It is a time varying parameter. Okay. But when we wanted to assign one number to that given vibration condition, Then you have to compute some parameter and then say this is the vibration level. For that, we will use commonly these three parameters. Up to this is clear. Yes, we have not gone into measurement at all. We are just learning the fundamentals towards. Of course, this is a well-known fact for you. I'm not going to talk much. If this is a sine wave, we call it as x, that's a displacement. Your velocity will be dx by dt. That will look like this. Of course, there will be a shift with respect to time. If it is a sine wave, the velocity will be a cos wave, and acceleration will be a minus sine wave. So you start. There is a shift of 90 degree in the graph. So this is displacement, this is velocity, and this is acceleration. Why I take that? Because that's another issue in acceleration. Whenever we have a vibration signal, we can measure the displacement because vibration is a special type of displacement, isn't it? Special type of displacement. If I am moving from here to there, we say I have displaced from here to there. We don't call I have vibrated from here to there. Why? There is no repetitive motion. But what is vibration? It's a repetitive motion with respect to a mean position. Okay? So the body or the scale, you take any point, it moved up, came back to middle position, moved down, came back to middle position, moved up, moved down. Basically it is a movement. Basically it is a displacement. You take a point in that body. Even if it is circular, there is an angular movement, there is an angular movement in the anticlockwise. So basically vibration is a special type of displacement. Okay. The moment it is a displacement, we can define velocity, we can define acceleration. Which one we will measure, which one is appropriate to measure depends upon the application. Okay. So it's not that we predefine and then go and measure. Depending upon the application, we will decide. So for a mathematical representation, simply if I take displacement as a sine omega t or a sine 2 pi f t, 2 pi is constant, f is frequency, t is time. To take that, find out the velocity, it will be 2 pi will come out because it is constant, and of course f is also, and a is amplitude that remains. Then you differentiate it, becomes cos 2 pi f t. So this becomes your velocity. Similarly, you compute acceleration. I have ignored the sign. You have a. Again, one more 2 pi will come, so it is 4 pi square. F will come, so it becomes f square, and sine 2 pi omega t or 2 pi f. It's like this. Of course, I am not teaching the basic differentiation mathematics, but that's the different displacement, velocity, and acceleration. Look at the amplitude of those parameters. When I look at the displacement, if I am measuring the displacement, the amplitude is decided only by a parameter called a. A is amplitude of the signal. Okay. If displacement is there, it will have the amplitude, so that will be there. Whereas, if I measure the velocity, that will be a function of a into 2 pi, that means about 6 times of amplitude. That itself is a good amplification. And f. F means what? Frequency. F means frequency. So, as the frequency goes higher and higher, amplitude of that particular high frequency signal will be higher and higher. For smaller frequency signal, the amplitude will be small. For higher frequency signal, the amplitude will be higher. So proportional to the frequency, my amplitude will increase. In certain case, that is advantageous to use velocity as a parameter because I am having the greater amplitude because of 2 pi and a. Instead of a means what? Amplitude. 2 pi means roughly 6 times, isn't it? Pi means 3.14. 2 pi means 6.28, something like that. Let's say 6 times. 6 times a. Is it difficult? Is it easy to measure a or 6 times a? It's easy to measure always a bigger quantity than a smaller one. Okay, very minute things I am talking about. So very difficult to measure very minute vibration. If the amplitude is big, it's easy to measure. Okay. In that way, velocity is easy. Also, as the frequency goes up, my amplitude of higher frequency signals goes up. Okay. In certain application, it is advantageous. In certain application, it is disadvantageous. Okay. So you have to look what is my application. Accordingly, I have to choose which parameter. Look at the advantage of displacement. If I am measuring displacement, I am not partial, I am impartial. Whether it is low frequency, high frequency, I give same magnitude, A. Whether it is a high frequency signal or low frequency signal, I am not amplifying, I am not showing any partiality in measurement. So, my signal will be exactly mapped to the displacement. If the amplitude is big, here it is. It is small, then this. Okay, whereas here, the amplitude is partial towards frequency. A low frequency fellow, a beggar comes, I treat him differently. A high frequency signal, a royal fellow, rich fellow comes, I treat him a royal treatment. My treatment is different for frequency, with respect to frequency. Okay. So here I am partial, but advantage is I have a big amplitude, also it is proportional to frequency. That's a characteristic. We don't say it's good or bad. In a given application, if it is useful, I will use it, otherwise I won't. Look at here. It is 4 pi square. Pi square itself is something around 10, right? 3.14 into 3.14 will be about 9 point something. So let's say 10 roughly. 4 times of 10 is 40 times amplitude. So amplitude is very high if I measure acceleration. If I measure acceleration of the vibration. Okay, that is why generally we measure any vibration, we measure acceleration. And the device which is used for measuring acceleration, we call it as accelerometers. Acceleration is measured, that's why it's accelerometers. In your syllabus also, the keyword given for vibration measurement is accelerometers. The very reason is, if I want to measure displacement, amplitude is less, velocity is little high, acceleration I have 40 times of amplitude. That makes my job easy to measure. So people use acceleration. Also look at one more. I draw your attention to F square. My goodness. F itself is partiality. F square is double the partiality. Okay. If something like, if somebody is having a lower frequency, I treat him very badly. If somebody is having higher frequency, I give exaggerated output to them. Okay. Higher and higher the frequency. For example, 2 Hz signal, 2 square 4, that is the amplitude. Whereas 20 Hz signal, 20 into 20 is 400 times I will show the output. Very exaggerated output I will show. So that is that it will be useful. Whenever I have some high frequency signals that I am interested in, mostly we are interested in high frequency signals, not low frequency signals. Whenever I am interested in high frequency signals, I am least bothered about the low frequency signals. If the application is like this, then the best parameter to measure in vibration is acceleration. The best parameter that we measure is acceleration. Why acceleration becomes so common? Because normally the rated speed of motor, rated speed of fan, most of the motors that's available commercially is at least 1440 rpm. You might have heard around 1400 rpm. Okay, 1400 times it will rotate in 1 minute. That's actually a high frequency signal. That will produce high frequency signal. Okay, and for such machineries which is operating with that much of speed, the amount of vibration we get are all high frequency signals. So we should worry about acceleration signal for those machineries. We are all engineers working with machines operated at 1400 rpm. So we will be generally concerned with acceleration. Suppose if I have a machine which is operating at 5 rpm, 2 rpm, 3 rpm, things like that, we will not be interested in acceleration. We may be interested in displacement. Because this sensor will give a better output for displacement measurements. For middle range of frequencies, velocity is the best parameter. to use for measurement. So whenever you go to a company, you have a situation to measure. You want to decide whether you want to measure displacement, velocity, or acceleration. What is that you should look for is what is the frequency content that I am supposed to measure, or what is the range of frequency that I am supposed to measure. If the range of frequency is very high, close your eyes, measure acceleration. If the range of frequency is very less, for example, seismic displacement, earthquake, or there is a movement of bigger stones under the earth, some sound will come actually, tsunami, or because landsliding, or very low frequency, slowly only it will move. So the frequency will be 1 hertz to 5 hertz. Those movements are better captured with displacements. Medium velocity, slow speed, 60 rpm, 50 rpm, slow speed. For example, you have a wind tunnel or a wind turbine. Okay, most of the wind turbines rotates a bit slowly. Of course, that slow speed is converted into high speed because of the gear train and power is generated. But most of the big wind turbines rotate slowly. So the bearings on that, if you want to measure the vibrations, you go for velocity. Wherever the rotation speed is high, the frequency that is generated is very high, you go for acceleration. I have covered two things. One, if at all some vibration is there, if I have to measure, first I have to decide whether I am going to measure peak to peak, RMS value, or average. Once I decide that, then peak to peak of what? Peak to peak of displacement, peak to peak of velocity, peak to peak of acceleration that I have to decide. Or RMS value of displacement, RMS value of velocity, RMS value of acceleration I have to decide. So once I finish this parameter, then I come to displacement, velocity, acceleration. Here you choose according to the frequency. Up to this is clear for all of you? Any confusion? Anything you want to ask me? Any doubts? Alright? Clear? Okay. So I have decided what parameter I have to measure and whether I want to measure displacement, velocity, or acceleration. Displacement, velocity, acceleration of vibration, because vibration is a type of displacement, okay? Type of motion, special type of motion. Motion is described with displacement, velocity, and acceleration. Quickly, I will take an industrial case, explain whatever we have discussed, the relevance of that, then we will go for measurement device. Learning measurement device is easy than understanding the context and where it is to be applied. Okay? So now, this is the displacement. You see, for the same displacement, this is the acceleration. This is the velocity, and this is the acceleration. You should know, normally, the x-axis will be time, y-axis will be amplitude when we plot the signal. But here I have plotted the frequency. X-axis is frequency, y-axis is displacement. X-axis is frequency, y-axis is velocity. Frequency, okay. Look at here. This is the actual displacement. These are all high frequency signals. When you go high, this is 2 hertz, 6 hertz, 10 hertz, 12 hertz. They are all 11 to 12 hertz. No, these are. In machine fault diagnosis, as a case study, machine fault diagnosis means what? Or machine condition monitoring. I want to know whether the fan is running, every parts inside the fan is good or bad. You are able to hear some noise, tick, 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 some noise, especially this fan. I don't know whether you are able to hear, but here if you come, you will be able to hear. That's because there is some fault in the fan. Because of that, that sound is coming. Also, if you put an accelerometer and take signal, the signal will be different from a new fan or a fault-free old fan of same age. This will have different vibration characteristics. Normally, that variation will be in high frequency signal. Normally, that variation will be in high frequency signal. So, we are interested in change in the high frequency signal. Change in the high frequency signal. Because of rotation, 1440 RPM, there will be a rotational frequency, okay, 2 pi n by 60, whatever, that omega. There will be omega corresponding to that. That will not change. As long as the fan is rotating at that particular speed, the rotational frequency remains same. If the health condition of the bearing or any other component in the fan changes, the high frequency content coming out of that body will change. For instance, let's say these signals, let's say this is corresponding to some fault in the rotating fan. So when I am doing fault diagnosis, I am interested in knowing whether my fan is good or it has developed some fault in it. So basically, I want to know what is the magnitude of this, whether it has grown up big. If there is no peak at all, here it is actually small, it is ignorable, then I have a threshold. Up to that, the fan is in good condition. If it starts becoming a peak, then it has developed some fault. Okay, that is what I wanted to see. Now I have taken a faulty signal. I have plotted here. When I see in the displacement, see a small, what is that? Projection or a small height here. Okay, that's not quite readable easily. Velocity is little amplified. Same signal velocity, same signal acceleration, you see it is greatly amplified. You will be able to see what you will be able to measure easily. You will be able to say, yeah, this, that. You will be able to make a decision quickly. Okay, so whether if this is 0 or it has reached a threshold, measuring here is difficult. Same signal in acceleration, measuring this will be easy because it is amplified multiple times, the higher frequency. At this moment, at this the case study, I am not interested in the low frequency signal at all. Here what happens, I am not bothered at all. Only if case is like that, I am only interested in the high frequency signal. So frequencies of 10 Hz, 12 Hz. I am interested in modifying. For a good fan, maybe that fan, let's say it is not making any noise, perfectly smoothly running. This peak will be very small here. This small peaks. For a faulty fan like this, the high frequency signal amplitude will change. Only that amplitude will change. I am looking for that by a vibration signal. So I will be able to, if I use acceleration of the vibration, I will be able to easily locate and then say, yes, this fan is faulty. Yes, this fan is not faulty. I will be able to make quick decisions by using acceleration. I can do the same thing with velocity also, but a bit difficult. I can do the same thing with displacement also, but very difficult. Because with no vibration, always there will be something called noise. And noise also will have the same frequency sometimes. So whether it is a noise or the signal, it is very difficult to find out with the displacement because the amplitude is too small. When I am interested in only high frequency signals. Whereas here it is moderately difficult. Here your job is made very easy. So you should look at what is the type of, what is the range of frequency that you are interested in. If that falls, if the frequency of interest falls in high frequency range, you should choose acceleration. If the type of the frequency is in the mid range, here, if your interest range is here somewhere, you should choose velocity as the parameter. If your interest is of low frequency signal, you should choose the typical example of this. You have a typical gearbox, put an accelerometer, take time domain signal, do FFT. FFT you have heard of it? Fast Fourier transform. You heard of Fourier transforms? Yes? What is the role of Fourier transform? Sorry? It converts? Sorry? Variable? What variable to what variable? No, it's not linear to angle. Sorry?
Sine cos. Sine cos.
That's Fourier series. Same thing, but okay. And your mathematics teacher would have not told you this. The Fourier transform transforms time domain signal to frequency domain signal. What is expressed in time domain, the variable t, will be changed to variable omega. It is not linear to angular. It is time domain signal to frequency domain signal. In time domain signal, the x-axis is time. You express the signal with respect to time versus amplitude. In frequency domain, x-axis will be frequency, so frequency versus R. Okay. So Fourier transform transforms this signal from time domain to frequency. Right. Up to this is fundamentals. Half an hour we spent on learning fundamentals. We have not gone to device. Actually, your syllabus talks more about this device only. Since vibration measurement is my research area, I have talked a little extra than your syllabus. Now, the device part of it, what are all the devices that can be used for measuring acceleration? You have plenty. I have listed few of them, which is commonly discussed in the textbooks. Elementary accelerometers, not used in Stone Age time, people have used it about 50, 100 years back. Now nobody uses such things, except some very rural industries where they don't have any accelerometers. For some crude measurements people may use, otherwise it is not used. But anyway, as a principle, I wanted to spend 2 to 3 minutes and then explain to you the elementary type accelerometers. Seismic accelerometers are still in use, and electrical type accelerometers are in white use. So we'll be talking more on that. Piezoelectric accelerometer is what is the widest. You take 100 accelerometer measurements, 80 to 90% of them will be based on piezoelectric because of its high dynamic response of the piezoelectric accelerometers. Elementary type accelerometer, it's pure mechanical, so you will find it very easy to understand. Nothing very good. I have drawn this not to scale. Not to scale means what? What is supposed to be very big, I have made it very small. What is supposed to be too small, I have made it very big. Because this is the point of interest, so I have enlarged this 100 times than the turbine. Turbine is actual size. The measurement device I have zoomed it 100 times. Okay, so you should not get confused, sir. Big turbine itself is so small. Is it such a big measurement system that we have? No, it is not to scale. Okay, that's a disclaimer. Here you have a plunger which is spring loaded. That means when the turbine is having a horizontal vibration, that vibration is transferred to one side of the lever, which is spring loaded. So whenever the lever moves horizontally, this moves horizontally. This is spring loaded. Here it is spring loaded. And the other side of the lever, you have a pen and you have a rolling paper. The rolling paper represents the time. Rolling paper represents the time. And the plotter keep plotting according to the vibration. If there is a small vibration, there will be small with respect to the V position. If there is a bigger vibration, there is a bigger vibration. You take the scale, which is a graph, which is normally plotted in a graph sheet, you will be able to directly read. Such accelerometers are not in use now. They're all very initial days people have used. The trace of the vibration signal is available, very inexpensive, self-generating. That means no need of electricity. Disadvantage: it has big moving parts, so wear and tear problem will be there, inertia problem will be there. High frequency it cannot be used, only low frequency you can use. All those are all. Plunger is constrained to one direction, so it is only horizontal vibration can detect. Three-dimensional vibration, three-axis vibration you cannot get in the same time. There are disadvantages. Acceleration level indicator. This is the vibrating body. The body is only this much I have shown. What is shown in blue color. Actually, body will be big. Maybe this is the vibrating body. This will be the body. Simply the sensor will be placed here, stuck there. This is a cantilever beam with a mass, and here it's a part of the arrangement. You have a screw and a circuit like this. The circuit is normally closed. A battery, the contact goes like this, goes like this. Through NOT gate, it is connected to relay and then a buzzer. Through NOT gate. Okay. When circuit is closed, there will be a flow of current, and the NOT gate will give you no output, so buzzer will not make sound. Here the vibrating body vibrates vertically. A cantilever will, it's a spring material basically. It is touching the nut up to certain level of vibration, it will be able to withstand. But when the vibration level is high, it starts coming out and touching, coming out and touching. There is an intermittent connection here. That mass, because of mass, it goes up and down beyond certain vibration level. That level is decided by how much you have tightened this and kept by the screw. Okay, that level. So for a given machine, up to certain level of vibration is tolerable. The machine is working fine. If vibration is going beyond that, you wanted to know. You want some buzzer sound should come. For that, you use this. So the vibration level is set by the screw, beyond which it starts coming out and then going and touching. When it starts coming out, it is breaking the electric connection. When it breaks the electric connection, that means there is no voltage. The NOT gate will give, when no voltage, it will give output. When output is there, there will be a buzzer, a speaker which will make pop sound or piam sound. So you will be able to get those indications that that machine vibration has exceeded the set limit. So there is something problem in that. So they go and attend to what is the problem in an industrial process. Again, these kind of devices also not used is very common. This is also a crude type of instrument. This is also not drawn to the scale. I have enlarged this some 1,000 times compared to the turbine. Okay, turbine is much bigger object, whereas the brittle member and mass will be like my finger thickness. Typically, my finger thickness. It is a circular body with a mass on top. Let us say whether it is vertical vibration or horizontal vibration, some vibration is there. It is a brittle member. What is the characteristics of brittle member? There is a mass on top of it. When the mass is moving, the element is trying to bend. The element is trying to bend. Up to, because the member is brittle member, it will not yield, so it will not bend. Up to certain vibration level, it will try to hold, it will try to resist. Beyond the vibration member, what will happen to the brittle member? It will break. That is what it will do. So wherever we want, it is a destructive type of device. Only once we can use it. Then we have to put another member and then stick. So you stick this kind of sensors or indicators, vibration indicators, in a big devices like turbines. When the vibration level goes beyond a tolerable limit, these indicators will fail, or break and then fall. Observing this, you understand the vibration level crossed the limit of set limit. Go and then stop the turbine and see what is fault inside. So those are all elementary type. Next type is seismic type accelerometers. Seismic means low frequency signals. Low frequency signals you can measure by using a spring mass damper system. Spring mass damper system. You have a spring, you have a damper or mass. How many of you have done a course on vibration? Nobody, yeah? My goodness. Okay. Or theory of machines, kinematics of machines, where you at least heard about this semester you are studying. Okay, maybe fag end of the semester you will be studying about vibration, where you will be familiar with spring mass damper system. Okay, so I thought you have studied already. So you have a mass and a spring and a damper. So when the body vibrates vertically, what happens? The mass will come and go inside the sensor. Okay, if the vibration is high, the mass also comes and goes faster. If the vibration is low, the mass comes slowly with a little amplitude. The movement will be less. So that movement is measured by LVDT. LVDT will give you an electrical signal proportional to the linear displacement here. If the displacement here is small, voltage here is small. If displacement here is more, the voltage. We have LVDT in our syllabus. Tomorrow or next class we will be talking about more details about the working of LVDT. So basically proportional to the vibration, you get the electrical signal. The idea remains same for all type of vibration measurements. This is a strain gauge type. You have a body. This is what is shown in purple color is the accelerometer. This is strain gauge type accelerometer. where there is a cantilever beam, there is a mass. Always there has to be a mass. Then only you can convert the vibration into a force. You can convert vibration into force. Because F is equal to ma. We are interested in A, acceleration. You need mass in order to convert the acceleration into force. So that force is applied here because of mass is there, it is converted into force. Because of force, this oscillates with respect to this point because this cantilever is attached here. When beam is bending either down or up, here there is a bend, there is a stretching here, either tensile or compressive in nature. Put a strain gauge, measure the strain from there. This strain will give an electric signal proportional to your vibration. This is capacitive sensor. Here you have one plate, here you have another plate. Did we talk about capacitive transducers? Not in the syllabus? Okay. Capacitor transducer, you have two capacitor, parallel plate capacitors, two parallel plates. One plate, another plate, they are parallel plates. The capacitance is given by epsilon naught, epsilon r, A divided by D into L. Okay? So that inversely proportional to the distance, directly proportional to the common area. Epsilon r is relative permeability, epsilon naught is absolute permeability of the free space. They are all constants. Okay. Epsilon r is given by the dielectric constant of the material in the between. Even air is a dielectric medium, paper is dielectric medium, mica is a dielectric medium. Those can be used in between parallel plates. So they are all here. What happens that it is inversely proportional to the distance. Here only that principle is used. When the cantilever beam is oscillating proportional to the vibration, the distance here changes. When distance changes, the electric signal changes. By properly calibrating, you will get signals proportional to the vibration. LVDT type, you simply keep the LVDT like seismic mass. In seismic mass, we have a spring separately, damper separately, and a mass. Here, they are all inherent inside the cantilever beam. You put a LVDT and measure the LVDT output. Piezoelectric type is what that you have to learn in detail, but there is nothing big to learn. Widely used. Okay. What is widely used? Piezoelectric principle is piezo means force, electric means you know electric. When a force is applied onto the two parallel sides of a crystal, on the other two parallel sides electric charges are developed, and vice versa. This principle is called piezoelectric effect. In vibration measurement, what we do is we make some provisions by which we apply force on two parallel sides of a piezoelectric crystal. And whatever is the charges developed, that we take, tap it, amplify it, and measure vibration proportional. This is the principle of accelerometer based on piezoelectric crystals. Some of the commonly used piezoelectric material are quartz, porcelain salt, barium nitrate, zirconate, or that. The beauty of this sensor, it has very high dynamic weight. Of course, for a typical sensor I have referred from the net is 5,000 Hz to 25,000 Hz. That means 25 kilohertz of vibrations you will be able to capture without loss. What is meant by 25 kilohertz? In 1 second, 25,000 times if object goes up and down, you will be able to capture all the motion without any loss. It's so sensitive to the frequency of high frequency signals. That's why piezoelectric signals are widely used. It can be used up to 350 degrees Celsius. This is the cover. This is the piezoelectric ceramic that we have. This is the body. There are three types of force that is applied. If the force is applied in shear mode, it is a shear type accelerometer. If it is compressive type, it is compressive type accelerometer. If it is bending, it is bending type. I told you, acceleration is what we are interested in. Acceleration is converted into force by using a mass, and you use any one of this piezoelectric type here. It can be conical type for shear, it can be for compressive, it can be for bending. That's a piezoelectric type of material. Of course, mounting and advantage and disadvantage will be those spec kind of. So these are all the basic things at least you should know about vibration machine. Probably next class, starting a few minutes, I'll talk about the mounting technique. Then we will go about.